we're going to consider another example of proving the correctness of a DFA. So previously we had considered this example where we designed this DFA, but we didn't actually prove that it was correct. So we're going to consider a DFA. I'm going to call it, I won't give it a name quite yet. DFA, we're going to design a DFA that accepts binary strings with at least 3 ones. At least 3 ones. So what did that DFA look like? Well, let me show you. Remember, we used this strategy of coming up with a pathway so that we can ensure that it has at least that many. But if it had more, we can have some flexibility what we could do with that. So similar to the example we had with substrings, we came up with a pathway approach like this, where we have a path where we had 1, 2, 3, so we had a path with 3 ones to represent having to read at least 3 ones. So you have to read at least 3 to get there. And then you can have more, right? So you can have 0, 1. So this was the DFA that we had last time. When we were designing the DFAs, this is one that we did consider when we were designing. So let's think about some state invariants for this DFA. So for each one of the states, we would like to come up with something we can say during any time that's being processed some string W. So let's think about state invariants. So remember, these are properties that are true during the processing of the string W. So when I process string W, it has to satisfy this property. So I want us to have an if and only if relationship, and if I can show that this is held at any point upon processing string W, it has to at any one string W, right? So, and naturally we could use mathematical induction to ensure that it is being satisfied, well, satisfying at least one of the invariants. In fact, we would like to have it where it satisfies exactly one of the invariants and none of the others at some point for a given string. We don't want them to overlap, ideally, because otherwise it gets harder to tell which state it's in, okay? So we have delta hat Q0W is 0. So, of course, when I process string W, it could be that it goes to Q0, right? So we're going to consider each one of the states. So I would like to say something meaningful for each one of these. So I have Q0. Upon processing string W, I would like to be able to say something about Q1. And upon processing string W, something about state Q2. And of course, something for Q3. So let's think about this carefully. Okay, when I'm in Q0, how many ones have I read? How many ones? Exactly 0, right? So maybe a nice state invariant might be that if you process string W and you're in Q0, that means that you didn't read any zeros, right? It means that W contains 0 ones. That's true, right? That's at least what we would like to say is true. We're going to actually prove this. But most certainly, that seems to be sensible, right? Then next we read, let's look at Q1. Well, Q1, now I want to bring up something really important for us to talk about. So, and this comes back to our discussion about proving the correctness of a DFA and this idea of state invariance. So when I have, for example, some different numbers of ones that I've read. I could have no ones. I could have at least one. I can have at least 2 ones. I can have at least 3 ones. I could have at least 4 ones, for example. But the point is if I read 4 ones, you'd agree with me that there's at least 3 ones, right? But here's where there's a little bit of a predicament, okay? A tricky point is that if you had 3 ones in a string, you would agree with me that it has at least 2 ones in it, right? So we need to be careful about how we formalize our state invariants, right, Miss Kitty? Yeah. Yeah, she had to smell it. So we're going to have to be careful about that so that the two, like when we list out these state invariants, we want to make sure that no 2 are the same. Like they don't contain the same set of strings. Otherwise it gets harder for us to prove our claim. It may be a bit too tricky. I don't know. But the point I'm getting at is that if you were to write something like this, if and only if W contains at least one, and we know that Q3 is going to be, oh, I forgot our accepting state. It's right here, right? We accept at least 3 ones. So Q3 is the one that we're interested in. You know right away a pretty good guess of what the invariant should be here is that it contains at least 3 ones. Or in fact, I'll write 3 this way. It's a little less confusing. At least 3 ones. Now, do you see that really, if I wrote this for Q1, you would see that these 2 actually overlap each other. Because anyone that has at least 3 ones most certainly has at least 1, right? So instead of saying at least 1, we want to say it contains exactly 1, because that does not fall into this category. It's a different set of strings. Now we can naturally do the same thing with Q2. So W contains, instead of add, I'll go contains exactly 2 ones. So notice that 0 ones, exactly 1, exactly 2 ones, at least 3 ones, so 3 or more. So you can see that any binary string would fall into any one of these, but I've covered them all, right? There can't be a binary string that doesn't fall into one of these buckets. Likewise, they're all their own thing, right? So just please be careful about that when you're thinking about your state invariants. Now, something I really want to show you is actually I can refine this list. Do you notice that there's actually a really nice structure about my states, how I index them, and also how many ones appear? So what I was going to suggest is that we can actually refine this list. So I'm saying that we could do much better than just this. In fact, I can break this down into listing 2 invariants where one of them encapsulates a good subset of these states and one for the other one. So check this out. So what I'm going to suggest is we're going to refine this idea. We're going to keep the bottom one. We're going to keep that one. So first we're going to have 2. So for all 0 less than or equal to k is strictly less than 3, we can actually state the following invariant. For state qk, it's that delta hat q0w is equal to qk. For what reason? For what reason? Let's think. W contains 1 exactly how many times? K times. So please just note that I'm just contracting all of that listing of invariants down to just this, and I do it over a range instead. So notice that this actually captures what I just wrote in those 3 other state invariants. This just contracts them all down into a single one, but it enumerates it over these, so it's the same exact statement. It's just more concise, and if I can write it more concisely in a way that it has a form like this, when you see the dreaded M word, or the mayonnaise or mustard, the stuff that makes a good sandwich, it tells you right away that, hey, look, maybe if I have it in a much simpler form like this, I can break it into even simpler cases as opposed to enumerating so many more cases. Likewise, do you notice that there's actually a nice structure to this? Do you notice that we actually talked about this when we were designing this DFA originally? We actually discussed, okay, well, what if I wanted to design a DFA that accepted at least 4 ones? And the conclusion that we came to together was that we could just add another state in here, and instead of having it going from Q2 to Q3, we would go from Q2 to this new state to Q3 and have the same structure as one of these states here. So we can actually extend this idea further, and that's actually what I'm going to do now. So rather than proving the correctness of this DFA, I'm going to actually prove the correctness of a whole family of DFAs for a given value that tells you how many at least you see of 1s, okay? How many times a 1 appears. So let's do that now. So instead of proving it for just this, let's prove it for a much broader one. So for constant k greater or equal to 1, design a DFA that recognizes the following language. We're going to call it, actually, instead of k, let's go with f. I'm going to call it f. It sounds like f for frequency. So I'm going to call it L at least f. So this is for a fixed f. So it's a set of all binary strings such that W contains at least, I'll say contains 1 at least f times. So that's L at least f. That's what I'll call it, L at least f. Do you notice that if f is equal to 3, that's exactly what we had before? Does everybody see that? So now what I want to do is show you how you could design a DFA that is good for this one. So let's just quickly whip this out. So it's the exact same idea, but it's based on the discussion we had last time. So I can have a start state. And remember, the pathway is I want to have this happen where I have to read at least f ones. So I'm going to have a pathway of 1s all the way up to state qf minus 1 with qf like this. Qf is going to be the final state. You can keep reading 0s and 1s. Got a 0, 0, 0, like this. Do you notice that if I make f equal to 3, you'll notice that this is exactly what we had before, right? This is the transition diagram for such a DFA. And my claim is that this is the transition diagram of a DFA that indeed recognizes L at least f. So now let's state the state invariance as a lemma. So now I'm going to just take the exact same thing we have here. I'm going to prove the following. Lemma. Consider integer. Consider f greater or equal to 1. Given DFA. Actually, for now, I'm just going to move this out of here so I can get a little bit more space. My apologies. Just that. And I'm going to call this DFA M at least F, because I have L at least F, then I could have M at least F, because this DFA depends on some constant F. And every W, which is a binary string, where 0 is less or equal to K is strictly less than F. So now what we're saying is for where K is going to vary from 0 up to but not include F. So 0 up to F minus 1. Now look at what we have here. Do you notice that I didn't change anything here, right? Except now I just changed this. Instead of it being Q3, now it's QF. Right? So if and only if a W contains one exactly K times, and QF is when you have it where what? Oh yeah, we have to change that to QF too, right? We're thinking about how we can generalize our ideas here. If and only if W contains at least, instead of 3, we want this to be K. At least K once. Or is it K? Is it K or F, guys? It's F, right? You'll notice that the indexing of the states tells you how many ones have been read. If you notice that right away, you're all good. That was by design. So there we go. There's our lemma. We're going to prove this using mathematical induction. And upon doing that, we can just simply observe what the invariant would tell us for QF, which this is that guy up there. So let's prove the claim. And you're going to see that this is surprisingly simple because we observed that there's actually a behavior in our DFA that happens over a whole bunch of the states. Almost every one of the states has this invariant, right? So rather than exhausting every one of them, I'm just going to contract them all into one state invariant that actually varies over some variable. And as long as I can prove it over that variable, we're okay. And you'll find it actually comes out much slicker than you would otherwise perceive at first. So, as usual, I got to tell you the game plan. To prove the claim, we use mathematical induction. Mathematical induction on the length of the string W. So on the length of the input. Now, let's do the base step. Remember, this is when we have the empty string. So this is when we have a string of length 0. So in this case W is equal to the empty string. And now let's just see what, by definition, the extended transition function will do. So it doesn't have any input to read. Which state is it going to be in? And delta hat Q0 epsilon, it's going to stay in Q0, right? As W contains no ones, it satisfies the invariant. It satisfies the invariant for Q0, right? Now, let's do the induction step. So we're going to fix n greater or equal to 0, and we're going to let the length of the string W be n plus 1, assuming, and remember this is very important, assuming the statement is true. The statement, as in the statement of our lemma, is true for all strings of length n. So that's our induction hypothesis. So we're going to consider now an arbitrary string w, and we're going to decompose it into two chunks. So as we've done before. So consider an arbitrary string w is equal to xa, where a is the last symbol of w. So x is going to be everything but the last symbol. So we prove the statement holds for string w, right? Now we have string w in place, right? So this is the setup. But now remember, x is everything but the last symbol. So what length does x have? What's the length of x? What's the length of x? It's n, right? And the induction hypothesis tells us that the invariants all hold, the state invariants all hold. So let's just exhaust those. And then we're going to see how we can append the last symbol so that we get w. So, as x has length n, by the induction hypothesis, for all 0 is less than or equal to k is strictly less than f. It has to be that for that delta hat q0 w, not w, we want x is equal to qk if and only if f contains 1 exactly k times, right? And delta hat q0x is equal to qf if and only if x contains f or more ones. So at least f ones. So this is what we get from the induction hypothesis. So now all we got to do is extend to, we have to append a on. So what's a? Well, a could be either 0 or 1, right? Since a is either 0 or 1, what remains is to consider each case above. Now you're going to be very surprised if you're thinking, oh yeah, Dan's going to have like a giant laundry list like some of his previous examples. Well, this one we're only going to have three, that's it. So check this out. And this entirely has to do with the fact that we simplified the state invariants. We contracted them down. So the first case is when from q0 we read in x and it's equal to qk, so state qk, and we read as 0. Well, what can we say for every k? For every k, so remember now we got to say a statement about any arbitrary k, right? So for every k is equal to 0, 1, all the way up to f minus 1, it is that that delta qk 0 is equal to qk, right? If I don't read a 1, I don't advance the next state along the chain or directed chain. So I just stay in the same exact state. So that's a property that every one of these states actually have. And delta hat q0w, because I'm appending a 0 on the end, is going to be delta of delta hat q0x of 0. So upon processing x, then I transition on a 0. This is the same as me saying qk of 0. Because we stay put in the exact same state, right? Or are we thinking about this a little bit more carefully? Let's think about it. Yeah, we stay in the same state, right? So since x contains 1, exactly k times, so does w, as desired for state qk. So we're all good. Checks out, right? It checks out. So that's the first case. So now naturally the next case is when a is equal to 1. So what's going to happen in that case? So when it reads a 0, it always stays in the same state. When it reads a 1, for each one of the k, it's going to go to the next state. This is where state invariants become rather helpful. So this is when we have x. So upon reading x, we're in qk, and we have we're reading a 1 next. So again, we can state for each k the following. For each k is equal to 0, 1, all the way up to f minus 1, it's that delta. So we transition from qk on a 1 to qk plus 1, right? Go to the next one. So next one over, advances 1 along the directed chain. So now we have the extended transition function. Delta hat q0w is going to be delta of delta hat q0x upon reading a 1. Well, this is just going to end up being qk as per our case here. Then I read a 1, and that gets me to qk plus 1. Right? So let me just write out what that means over here. We're not quite done with this case. Think about what w is. So w previously contained k1s, right? And then we found another 1. So that means that w actually has k plus 1 many 1s in it. But what state is it in? qk plus 1, as you would like, right? That's exactly what we desire. Previously x contained 1 exactly k times. So w equals x1. That's what exactly the form of this one will be. Contains k plus 1 ones, satisfying the invariant for qk plus 1. Right? So that concludes the second case, and we have one last case to go. And you're going to be rather surprised how quickly, so keep in mind, those two cases collapsed a whole bunch of states. And it's all about the observation about how we formulated the state invariants. That's the main point of what I'm trying to present to you. is that you're careful about how you state the state invariants. You can get away with doing things like this, and you're not fudging anything. The thing is, you have to state something that's true about all of those states. So finally, the third and last case, because it doesn't matter which one it is. So remember, at the end of the directed chain, you have it where it reads a 0 or 1. It's similar to a previous example we had where it didn't matter. So these are going to just contract into their own singular case. So we end up in QF, and either A is 0 or A is 1. So in either case, delta hat Q0W is equal to delta of delta hat Q0X A, right? But we know what this is. This is QF. That's QF. But remember, regardless of if it's a 0 or a 1, it stays in QF. And since X contains 1 at least F times, so does W. And that completes the last case. So now all we have to do is conclude the induction step, because now we've considered all the possible situations. Thus, the statement follows. The statement follows for when the length of the string is equal to n plus 1, regardless what W is. So anyways, now, we're not quite done yet. We still have to invoke what? The principal of mathematical induction, right? We have to still use that. Therefore, by the principle of mathematical induction, the statement, remember that's a statement of our lemma, the statement is satisfied. Statement is satisfied for all strings. For all strings. That completes the lemma. Now, are we done yet? No, we're not done yet. We still have to do one last piece of this. We have to prove that the DFA is correct, right? So, but we have the key ingredient now. We've got this lemma. This lemma gives us these invariants. And all we do is we put our finger on which invariant is the one we need. We need the last one. So that's the little cherry that's going to go on top. So observe. So this is the end of the lemma proof. Now I'm just giving you the argument you would provide for the correctness of the DFA. So observe that the set of final states, F only contains QF, right? For our DFA M at least F. And for any string, W accepted by F by M at least F, keep it careful, satisfies what? What does it satisfy? Remember, I have to use the definition of what it means to accept by a DFA. That delta hat Q0 given the input string W is equal to QF, right? Therefore, by our lemma, because remember, to satisfy this means that there's at least F1s in it, right? That's what the lemma tells us. Therefore, by our lemma, W is accepted by M at least F if and only if W is in L at least F, which we defined a little earlier. So now I have provided the argument we need to state our theorem. So as I stated with our previous examples, this is the argument you would use to prove this theorem. Just to be clear, I just like to keep it a little separate. Just give a little bit of room, okay? So for any integer f, which is at least 1, so for any one of these f's, you define the language, right? Each language is associated with an integer, and each DFA is associated with this integer. So please just keep that in the back of your mind when you're thinking about this. So the language of M at least F is equal to equal to L at least F. And that concludes the example. So this is how we could prove that our DFA is correct. So we've seen a whole bunch of examples here of using state invariants to prove the correctness of a DFA. And remember, all of these languages that we've established and used in all of our examples, they're examples of regular languages.